All right, so in this chapter, we're doing something kind of similarly related to confidence intervals, but slightly different, which is hypothesis testing. So we'll use a lot of the same principles that we did in the previous chapter, just painting them in kind of a different context. So there we go. So kind of what are we wanting to do with hypothesis testing? So what we're going to do is first, we only have sample data, but we're interested in something about the location of what the population parameter is. So if this is the population mean or the population proportion, so there's something that we want to test. So we're going to develop what we call a null and alternative hypothesis. We'll kind of dive into these here a little more in a second about where this population parameter lies. We're then going to test, like look at our sample data to test these hypotheses. Um, and if we have enough evidence from our sample that it's not, the hypothesis isn't true, we can reject the null. If we don't have sufficient enough evidence, we say that we failed to reject the null hypothesis. Okay. So kind of our motivating example, when I'm coming up with this null and alternative, the alternative hypothesis is what we want to test. The null, we're going to assume the exact opposite is true, and then that's what we're going to test. If we find enough evidence that goes against the null, we can reject it, or we found evidence that supports the alternative, or we don't have enough evidence, we can't reject the null, we don't have enough evidence that really supports the alternative hypothesis. So kind of a dumb motivating example I've got. So let's say, I don't know, someone tells you that this beer, Bell's Two Hearted, has ABV of 7%, that the average mass market beer's ABV is lower. Right? So that's what you're wanting to test. Well, if I want to know, is that true population mean for these mass market beers, that ABV, is it less than 7%? What I'll do, or sorry, I take a sample of 36 and I find 4.5. So the null hypothesis is going to be when I assume the exact opposite of what I'm trying to find. So for us, we were trying to test for whether or not that average ABV was less than 7%. So we assume that it's greater than or equal to 7% for our null hypothesis. Okay. So I'm going to skip ahead here. Well, I got some other examples I'll go through. So let me just switch over. So in this example, what we're looking at here, and actually I gotta flip this around, is my alternative hypothesis was what I wanted to test, which was, is that true population mean ABV less than 7.0%? My null then becomes the exact opposite, which is greater than or equal to. So if we can find enough sample evidence that goes against the null and supports the alternative, we will reject the null. So kind of setting up this idea of null and alternative hypothesis, we'll look at it in a slightly different context. So I think I have like, what say here. So, just the kind of textbook definition here of whether or not we reject or we fail to reject the null. So there's three kind of scenarios. So one, I find sample evidence that's not consistent with what I assume to be true or not consistent with that null hypothesis. You can almost think about the null hypothesis as this is kind of like the assumed state of the world, or whatever example we're looking at. This is the assumed true value. So if I find something from my sample that goes against that, right, and it goes against it a lot, I can reject the null. Now, when I fail to reject the null, sometimes it's because I find sample evidence that uh, does support, like I could fail to reject the null because I found evidence that really supports the null or is consistent with the null hypothesis. Um, so it's not inconsistent. I guess shouldn't be using double negatives here. We could say that the sample evidence, oops, sorry, is consistent with the null. Right. So if I assume that the average mass market beer has a ABV greater than 7%, I take a sample, I find 8. Okay, well, that supports my null. So why would I reject it? Now, the more likely scenario is I find evidence that goes against my null, but it doesn't go against it enough, right? Now we'll make a little more sense of this when we start to talk about, okay, what does that mean? Not go against it enough. Well, we know this, if what we assume to be true is in fact true, we know that if we assume, say, that ABV is equal to 7%, well, then we know that our sample means should be distributed normally around 7%. So we'll dive into this a little bit more. There's kind of three scenarios. Inconsistent evidence with the null so that we can reject it. Inconsistent evidence with the null, but we don't have enough to where we can actually reject the null. And then sample evidence that's just consistent with the null, and so we would fail to reject the null there as well. So kind of stepping away from numbers for a second, maybe just to make this idea of null alternative hypothesis sink in a little bit better. If I think about like a court case, what am I trying to test? I'm trying to find if somebody's guilty, right? That's our alternative hypothesis. So what do we assume to, what should every court case assume? That you're innocent until proven guilty, right? So we want to find if the defendant is guilty. That's our alternative hypothesis, but we assume the opposite is true. We assume that the defendant is innocent. If we can find enough evidence that goes against the null, so we find enough evidence that the defendant in fact isn't innocent, maybe we find, I don't know, the murder weapon in their apartment, DNA evidence that they were at the scene of the crime, etc., then we reject the null. We reject that they're innocent and instead say we found evidence that supports them being guilty. And so you go to jail, right? What if you don't have enough sufficient evidence? So, maybe, there's no DNA evidence, but they don't have an alibi. They did have a grudge against this person that was murdered. So, we have some evidence that would go against that defendant being innocent, but it's not enough. Well, right, then we can't reject the null. We can't reject that the person is innocent and they're free to go. So that's I don't know, the court case analogy. If the glove doesn't fit, you must acquit or must fail to reject the null. Okay. So if we kind of return then to a more numerical example, our null and alternative hypothesis, we really have three different types of hypothesis tests that we're going to be using when it comes to population means and then eventually population proportions. So the first is what we call a greater than test. So the names, I guess, of these tests kind of come from the alternative hypothesis. So notice here, mu0, this is in practice when we work through the problems, this is going to be a value. So this was like when I said, I want to test for whether or not the ABV is greater than 7%. This would be 7. Right? So here, the greater than sign in my alternative hypothesis, it's a greater than test. I'm trying to find if the true population mean is greater than a certain value. I assume the opposite is true for my null hypothesis, right? H subscript 0 is my null, H subscript A is my alternative. I'll always use this notation. I think if you look at the book or you look at some of the resources, sometimes they'll write the alternative as H subscript 1. I don't know, it just makes it easier for me, I think, to put an A there. Less than, right, is the other type of test we have, which is instead of trying to find is the population mean above a certain value, we say, is it less than a certain value? We assume the opposite is true for the null, which is that it's greater than or equal to that value. Here we would call this a right or a greater than or less than test, or eventually I'll probably more reference them as a right tail and a left tail test. And that'll make a little bit more sense once I kind of show you some of the visuals. If we instead want to know, okay, is the population mean different from a specific value? So maybe I'm interested in like the number of, I don't know, the number of what car accidents on average of someone. I don't know, is it different than the value of 2? Well, that's not equal to, right? In my alternative hypothesis, I'll assume the opposite is true, which is that the true population mean number of accidents actually is exactly equal to 2. Okay. So here we would kind of call this not equal to a two-tailed test, right? Or a two-sided test. So right tail, left tail, two-tailed test is kind of a less technical way of referencing this greater than, less than, not equal to test. All right, so our steps, we first need to know, are we looking at a population mean or proportion? We'll see eventually why that makes things a little different. Is it a one or a two-tailed test? Some of the stuff we do with hypothesis testing will vary a little bit depending on if it's one of these one-sided or if it's a two-sided test. And then we need to make sure we always establish some form of equality on the null or alternative. Convention is really to include that equality here in the null hypothesis. And how can we kind of remember that? Well, for my two-tailed test, it literally is just an equality sign. So for my greater than, less than test, I'll make sure I include the equality in the null hypothesis as well. All right, so back to our example. Right? We wanted to test for whether or not the average mass market beer has a lower ABV than Bell's Two Hearted. So in English, what I'm saying is I'm going to assume the exact opposite is true because my alternative hypothesis is that the mean mass market ABV is lower, right, than Two Hearted, or is lower than 7%. I'll assume the opposite is true, which is that it's not lower, or that it's greater than or equal to 7%. So here, right, my null is that it's greater than or equal to 7%. And my alternative, the thing I wanted to try to find, is that it's less than 7. So if I can find evidence that goes against this null, maybe I can reject it, right? Well, remember, oh, sorry. Remember, we did have evidence. I think if I go back, it was 4.5% that kind of goes against the null. So maybe I can reject this null. All right. We haven't talked about, how do we determine if evidence is strong enough to reject the null yet, but we at least have something that's a candidate, right? If I had taken the average, sample mean average and I found 7.8, well, now I have something that supports the null. For sure, I'm not going to reject it. Just to kind of give you a different kind of setup thinking about these, let's say I wanted to determine whether or not the mean retirement age is different than 67. So anytime we're looking at like a word problem, we're thinking about testing something, and I'm just thinking, is it different from a specific value? That means what I'm testing for, the alternative hypothesis, is that the true mean retirement age is not equal to 67. I assume the exact opposite is true, which is that's exactly equal to 67, right? So here, my null and alternative hypothesis, I'd have this two-sided test. Okay. All right. So before we go into a little bit more of the mathematics behind what we're doing with hypothesis testing, we've got kind of this definition, or at least start to think about what we call type 1 and type 2 errors. Right? So a type 1 error is when, based off of my sample evidence, I reject the null hypothesis, even though I shouldn't have. A type 2 error is when I look at my sample evidence, I didn't reject the null, even though I should have been. Right? So you kind of imagine this would be the idea, like in the court case example, type 1 errors would be what? Well, those would be situations where we rejected the null, but we shouldn't have, or we rejected that the person was innocent. These would be people, type 1 errors are people who are wrongly imprisoned, right? We can kind of think about that. Type 2 errors, so this is going to be someone where we didn't reject the null, even though we should have. This is going to be someone who committed a crime and got away scot-free, right? So, maybe the glove doesn't fit. You must have quit, like from the previous slide, kind of applies here, right? So type 1, type 2 errors, you can kind of build this little kind of table. So here, did I reject the null or did I not? Was the null actually true or was it false? Well, if I reject the null and it in fact is false, I made the right decision. If I fail to reject the null and it ends up being true, well, yeah, I should have failed. That's a correct decision as well. However, when I reject the null, even though it was true, that's my type 1 error. And when I failed to reject the null, even though I should have been because it was false, that's my type 2 error. Okay. What we'll end up seeing is the process of our hypothesis test. Our type 1 errors are going to end up being whatever alpha value we have. So alpha here is very similar to confidence levels. So our proportion of type 1 errors that we're going to make is going to be, for our conventional levels of confidence, 90, 95, 99%. Alpha, the type 1 errors, the proportion of type 1 errors we make, 0.1, 0.05, 0.01. So very similar to what we're doing with confidence intervals. Another dumb example to kind of remember, type 1, type 2 errors, here you're telling someone, let's assume that the null hypothesis is that you're not pregnant. Here we're rejecting that null, saying that this person actually is, but clearly we know the true state, right? This person cannot be pregnant, isn't pregnant, and so we have a type 1 error. Type 2 error, someone who is very visibly, clearly pregnant, but we tell them, oh, we're actually failing to reject the null that you're not. Well, very clearly, I failed to reject when I should have, in fact, been rejecting. All right. So, we got type 1 errors. I already mentioned will be kind of alpha. The probability that I don't make a type 1 error is 1 minus alpha. This isn't anything crazy. We're using our conventional kind of alphas like we were with confidence intervals, 0.1, 0.05, 0.01. And type 2 errors are harder to calculate. We'll kind of look at them, think about what decreases the probability I make a type 2 error, larger sample sizes, lower levels of confidence, but I'll kind of set this up, thinking about why we make type 1 or how we make type 2 errors. So what I'm going to do, I think I'm going to draw this out for you. So let's say I've got that example we had before. What I'm going to do is say, okay, look, if the true mean was 7% here, what should be true about the distribution of my sample means? If the true population mean was 7%, then my sample mean distribution should be centered around 7%. Right? Now, if I just take one sample, right, maybe I see 6.7 as my sample mean, right? That's fairly likely. Okay, this technically goes against the null, but not very much, right? Especially if this has a relatively large variance. This isn't going to be very many standard deviations away. It's very, very likely I would see a sample mean of 6.7 if the true mean was 7. Now, seeing a sample mean of 4.5, well, that's quite a bit further away from that value of 7.0. In fact, how unlikely was it to see 4.5? Well, if 7 was in fact the true population mean, the probability I saw 4.5 or anything more extreme, or another way of saying this is what's the likelihood I saw the sample mean that I did, or anything that is even further away from that assumed true value of 7%. This is what we're going to end up calling our p-value. So this is just the probability that I saw sample evidence that was as inconsistent with what I assumed to be true or something even more inconsistent. So the probability that I saw sample evidence that was as inconsistent as I found or something even more inconsistent with that null hypothesis or the hypothesized true value. Okay. So if this probability gets relatively low, then I'm saying, well, it's very unlikely that this is the true value based off of the sample mean I found. It's probably way more likely if I found a sample mean of 4.5 that the true mean is going to be something closer to that, right? So this is the idea. We'll look at our sample mean. How can I find out this probability? Well, let's tile this together. I think going into a little different order than the slides, but I think this is good. So let's say we have that same setup. 7%. I found a sample mean 4.5, right? This is my distribution of my sample means. I can turn that into a standard normal distribution, right? So I can turn this value into a z-score, right? How can I do that? Well, I'll take the sample mean that I found, subtract the true population mean. Well, now here I don't know the true population mean, but I have an assumed true value for it, right? And then we'll divide by square root of variance over our sample size, okay? So this would all be information that we have from the problem. We then convert this into what we call a z statistic. So it's still a z value. It's just we call it a z statistic because it's representing how many standard deviations away from this assumed true mean is the sample evidence that I found, right? Then using that z value, it's just like what we're doing before. I can find the probability that I saw that test statistic or that z statistic or anything even larger, or any test statistic that's even greater in absolute value. So here, if I found something below the assumed true mean, I know that the test statistic will be negative. So anything out here is just a larger negative value, or, you know, more standard deviations below that assumed true mean of 7. So I can look this up in my standard normal table or use Excel as my kind of Z table, and I can find what we call the p-value. Right? Okay, so hopefully that gives kind of a nice visual. And you can imagine if this p-value starts to get low enough, we say we're okay rejecting the null. Right? So why is this case? Why are we okay rejecting the null? Well, if I think about, we said alpha is kind of the type 1 errors that I'm going to be making. So if I'm at the 90% confidence level, so the type 1 error was when we rejected the null, even though we shouldn't have been. So if we shouldn't have been rejecting the null because this was in fact the true mean, anytime we get a sample mean that's associated with a p-value that's less than whatever alpha we're interested in, those are all going to be valid. So let's say I want to make only 10 type 1 errors. I only make them 10% of the time, or an alpha of 0.1, right? So I know that the area I want in this tail is 0.01. Well, if this in fact is the true mean, then for all of these sample means, I'd be rejecting this null even though I shouldn't have been. So if the probability falls, and I put 0.01 here, sorry, 0.1. If the probability falls below 0.1, these are all going to be p-values less than 0.1. We said I'm going to reject the p-value is less than this type 1 error alpha I'm setting. So I will be making this amount of type 1 errors if what I assume to be true is in fact true, right? So that's the idea of kind of our type 1 errors, but we're okay. We're okay with that, right? Because the probability I'm making a type 1 error is really only, what, 0.1, right, or 10%. And we can increase this to say 99, or sorry, the 99% level, or only making type 1 errors 1% of the time, okay? So this is going to look a little bit different for different types of tests. So here's the one that we were just looking at. This was, excuse me, when I had, oh, where's it at? I'll skip ahead a little bit because I wanted to show you how to match it up. There we go. So here was our null and alternative hypothesis. We had a less than sign in the alternative hypothesis. Notice here, I use the different notation instead of A using 1, just so we kind of get a taste of both. Less than sign, left-tailed test. Well, notice if I'm looking at the p-value, there we go. Once I find this test statistic, or the number of standard deviations away that my sample evidence is, for a left-tailed test, being sample evidence that was more inconsistent was anything even further to the left. So there, my p-value is going to be the area to the left of the test statistic I find. If I have a right-tailed test, so remember, this is where I'm assuming that it's less than or equal to a certain value, or I'm trying to test for whether or not it's greater than. Well, now things that go against the null are going to be on the right-hand side, and evidence that goes even more against the null is going to be even further into that right tail. So here, my p-value is going to be the area to the right of my test statistic. Okay. And then for a two-tailed test, right, I'm only ever going to see the sample, one sample mean. So I'm only ever going to have one test statistic. But just to kind of give you, I think I can draw this one, make a little more sense. So if I have a two-tailed test, the distribution of my sample means here, I've got whatever the assumed true mean is. So just choose a number, right? If I found a sample mean that was down here, right? Well, the probability I found sample evidence that was as inconsistent with the null as what I found, or anything even more inconsistent, would be down here. But it would have been equally as likely if I don't have a one-tailed test sample evidence that was over here on the right-hand side would also go against the null. And even though I only took one sample and this is the sample mean I found, it would have been equally as likely I found something that was what, 5 above instead of 5 below that true mean. I'm sorry, assumed true mean. And any evidence greater than that also goes against the null. So with a two-tailed test, I can find the area in one of the tails, but my total p-value, each one of these tails only has half the p-value, right? I would add these two up to get my total. So once I have those p-values, then the kind of rule of thumb, if I can get a p-value that is, oh, I think I've got it. It's a separate bullet point here. There we go. That is less than alpha. Then I would say I reject the null at that level. Okay. So you can imagine for some things, I might end up with like a p-value of 0.07. Well, that's less than 0.1, so I can reject it at the 90% confidence level, but it's not less than 0.05 or 0.01, so I can't reject it at the 95 and 99%. Okay. This is kind of a summary of this, I guess a little bit more technical, right? But anytime I have a greater than or a right-tailed test, I'm looking for the probability I found the test statistic I did or anything even greater, right? I'm looking at that right side. Less than left-tailed test, I'm finding the probability that I found the test statistic that I found or anything to the left of it. Two-tailed test, it kind of depends. I could find sample means on either side. I'm then going to just basically go find the area that's in the tail, which no matter which tail I'm on, and then multiply it by 2. Okay. And I think working through more problems is going to be helpful here. So one thing I wanted to point out, I'm glad I added this bullet point, is that the difference between a one and a two-tailed test, notice the p-value, because I'm getting multiplying by 2 here, the same sample evidence, if I do a one-tailed test, I'm going to end up with a lower p-value. Because if I found the same sample evidence, but I instead had a two-tailed test, I multiply that area in the tail by 2, I'm always going to have a slightly larger p-value. So it's a little bit harder to reject two-tailed tests. Okay, so we can get this to keep moving. There we go. So here's kind of my steps all laid out. We'll then apply this to that ABV example, look at a few more examples. So first I need to determine what my null alternative are, right? Do I have a right, left, two-tailed test? Specify my alpha value. I then will compute this z value, right? Turn my sample mean into a z value, or what we're going to end up calling a z statistic. Using that z statistic, we then calculate the p-value. And then once we have the p-value, we reject the null if it's less than alpha. Okay. So what's this going to look like for us? So we've got that same setup. I don't know why I changed the name of the beer here. But if we had one that was 7%, the numbers didn't change. So I've got 36 mass market beers. I find a sample mean of 4.5. I have a known population variance of 1, right? Just making it kind of easy here. Can I reject the null at the alpha is equal to, I put 5% level? Really, this to be technical, like our alphas should be in decimal form. And in fact, I have this in the slides later, but if I can spell, we end up saying that an alpha, oh, come on. There we go. An alpha of 0.05 would correspond to what we say the significance level of 5%. Okay. Oh. So determine our null alternative. We kind of already talked about this. I jumped ahead to it earlier. We want to find is that ABV less than 7%. So that's our alternative hypothesis. We assume the opposite is true, which is that it's greater than or equal to that value. We then say, okay, well, what was our alpha? We were told this was 0.05 or the 5% significance level. How do I determine my z statistic? This should be hopefully not terrible after all the stuff we went through up to this point, all the previous chapters. I'm just going to take that sample mean. So that was what, 4.5%. Subtract the assumed true mean. I get that value from my null and alternative hypothesis, so 7. I was told the known population variance is 1, sample size is 36. I get a z statistic of -15. I want to find what my p-value is. Now here, it's basically 0, but how would I do that? So two ways. This first way is going to be kind of hard to show you just because it was so extreme. But notice negative 15. Well, at negative 3.99, the area to the right of that is basically 0. So if I'm looking at the area to the right of negative 15, it's going to be even closer to 0. In fact, I can use Excel. And here I'll zoom in so we can see what I'm doing. So norm dot s dot inv. Actually, no, sorry. Norm dot s dot dist. I had negative 15. I want the cumulative probability. I want that area in the tail. E to the negative 51 means move that decimal 51 places to the left. So this is basically 0. So if my p-value is basically 0, am I going to reject the null? Well, we only reject the null if the p-value is less than alpha. 0 is going to be less than any alpha. So I could reject at the 5% significance level. I could reject if alpha was 0.01. This is really strong evidence that what I assume to be true isn't in fact true, right? I found a sample mean that was pretty far away from that assumed true mean. Okay. And then, classic meme to go with. I hate craft beer now because it's in. So we'll go to that second one example I showed you earlier and kind of show a two-tailed test p-value example. So let's say I want to know, is the mean retirement age, oh, actually, no, I didn't do a two-tailed. I did, is it, yeah, greater than 67, right? I've got 25 individuals. I find a sample mean of 71. Population variance is 81. What is the p-value of this hypothesis test and the rejection decision at the 95% confidence level? Okay. So I'm going to draw this one out. I think I've got it in the slides, but we might as well just work through this one together. So I wanted to test for whether or not the mean retirement age is greater than 67. So I've got my alternative hypothesis is what I want to try to test for. So I've got a right-tailed test. I assume the exact opposite is true, which is that it's less than or equal to 67. I'm going to think about then, okay, if what I assume to be true is in fact true, my sample mean should be normally distributed around 67. However, I saw a sample mean that was 71, right? So what I'm then going to do is convert that sample mean of 71 into a z statistic. Oh, I'm off the page here. Right? Once I have that z statistic, I can find the probability that I found sample evidence as inconsistent with this hypothesized true value or something even more inconsistent. Right? This is going to represent my p-value. I then compare it to alpha. So if I have set the 95% confidence level, my alpha there, right? Well, with 95% confidence, I know I'm making the right rejection decision. If I make the wrong rejection decision, that's a type 1 error. So if I'm making the right decision 95% of the time, 5% of the time I'm making a type 1 error. The way we usually kind of display our type 1 error or alpha is in decimal form, so 0.05. Okay. So I will work through this one and the actual values here in a second. Well, we'll come back to this. We'll work through the actual values, and then I'll return to this because there's something else I wanted to point out here. So we developed, right? We already identified this. What's the actual test statistic? Well, we had our sample mean, our hypothesized true mean. That value just came from the null and alternative. We were given a known population variance. We had our sample size of 25. We get a test statistic of 2.22. Right? What's the area to the right of that, or what is my p-value? I can do this two different ways. So I could say, okay, 2.22, so 2.22, 0.9868. So that's my p-value. No. You guys remember, this table tells me the area to the left of 2.22. I wanted, remember, the area to the right. That was the visual. That's where kind of drawing it out sometimes helps you or prevents you from making that easy mistake. So how do I find the area to the right? Well, if this is the area to the left, the area under the curve is 1, just 1 minus this. Right? So it's what going to be what about 0.0232? If I'm doing math in my head correct here. Now, I could have also used type the norm.s.dist function. Test statistic was 2.22. I want the cumulative probability. Once again, that's the area to the left of 2.22. I wanted the area to the right. So 1 minus that. Oh, I did do math in my head. No, it's not 0.02, it's 0.0132. Right? So there would be kind of my p-value. Okay. All right. So with that p-value of 0.0132, do I reject the null? Well, we said my significance level, alpha, is 0.05. So yes, this in fact is less than that alpha of 0.01. So here's just kind of in general the steps that we'll use. To instead of using the p-value approach, which we do here. Now, I think I wanted to point one thing out here, if I remember right. Yeah, the flow that I have this. So I did set, where is it at? Okay, I did ask you about a specific level here, but one thing I wanted to point out is it doesn't really matter. I don't really have to necessarily just do one hypothesis test. If I use the p-value approach, it's pretty easy to do a bunch of them right away. So once I know this p-value is 0.0132, I can compare it to a bunch of different alphas, right? Now my conventional alpha is 0.1, 0.05, 0.01. So what would my rejection decision be? Well, is this p-value less than alpha? Yes, so I can reject at the 10% significance level or 90% confidence level. Is my p-value less than alpha here? Yes, so I can reject at the 95% confidence or 5% significance level. Is it less than 0.01? Not quite. So I fail to reject the null hypothesis at that 99% confidence or 1% significance level. Okay. Another way of kind of thinking about this is when I'm saying all of these, so I've got significance level, I've got my confidence level, and I've got alpha. So usually we look at 90, 95, 99% confidence, 10, 5, 1% significance level, 0.1, 0.05, 0.01 is my alpha. What if I wanted to do the 85% confidence level? Well, that would be a significance level of 15, and my alpha there would be 0.5. Okay. All right. So